All right, geometry detectives, welcome. Today, we're cracking open a classic mystery, one that you've probably seen before, the case of the similar triangles. We're going to gather clues, use our detective's toolkit, and solve this thing once and for all. Let's get started. So, take a look at these two. At first glance, they seem connected, right? One just looks like a bigger version of the other. But in geometry, you can't just go on looks. The real question is, are they actually related? And how could we possibly prove it? Okay, before we dive in, let's lay down the law. Two triangles are called similar if they have the exact same shape, but their size can be totally different. For that to be true, two things absolutely have to happen. First, all their matching angles have to be equal. And second, all their matching sides have to be proportional, basically scaled up or down by the same exact number. Now, every good detective needs a toolkit, and we've got a great one. See, you don't always have to check every single side and every single angle. We have three super powerful shortcuts, our three rules of similarity, that'll help us crack any case we come across. First tool up, the AA rule. This one is so simple, but so effective. If you can show that all three corresponding angles in two triangles are the same, that's it. Game over. You've proved they're similar. The sides will just automatically fall into line. It's a fantastic shortcut. Next, we have the SSS rule. This one doesn't care about angles at all. It's all about the sides. If you can show that the ratio for all three pairs of corresponding sides is the same, like they've all been multiplied by 2 or cut in half, then you've got it. They're similar. And our last tool is SAS. Think of this one as a hybrid. You only need one pair of matching angles, but here's the catch. You also have to prove that the two sides that make that angle are proportional. So the angle has to be sandwiched right there between the two sides you're checking. That's the key. All right, we've got our toolkit. It's time to get our hands dirty and see how these rules actually work. Let's open up some case files. Here we go, case file number 1. We've got triangle ABC and triangle PQR. Looks like the evidence we've been given is all about the angles. Let's break it down. Let's look at the evidence. Angle A matches angle P. Both are 60 degrees. Check. Angle B matches angle Q. Both 80 degrees. Check. And angle C matches angle R, both 40 degrees. Check. All three pairs line up perfectly. There's really only one conclusion here. With all three angles matching up, this is an open and shut case. We can confidently say these two triangles are similar, and we've proved it with our angle rule. On to the next one. Okay, case file number 2. This one feels a little different. We're given two sides and an angle for each triangle. My detective senses are already telling me this might be a job for our SAS tool. Let's see if the evidence checks out. Let's run the numbers. The ratio of side MN to QP is 2.5/5, which simplifies to 1/2. Okay, now the ratio of side ML to QR is 5/10, which is also 1/2. Perfect! The ratios match, and the crucial part, the angle between those sides, angle M and angle Q, are both 70 degrees. The evidence is rock solid. We've got two proportional sides, and the angle between them is equal. This is a classic SAS case. Verdict, similar. This next case looks pretty simple at first. We've got all three side lengths, so you'd think we can just use our SSS rule and call it a day. But a good detective always checks all the evidence. Let's look at those ratios carefully. Okay, let's do the math. The ratio of MP to DA is 2/4, which is 1/2. Good start. The ratio of PL to DF is 3/6. That's also 1/2. It's looking good, but wait a minute. Look at the last pair, LM to EF. That's 2.7/5. That is definitely not 1/2. The pattern is broken. And because that one ratio doesn't match, our SSS rule doesn't work. The whole case falls apart. So even though they might look kind of similar, the math tells us the truth. Verdict, not similar. And you know, finding out they aren't similar is just as important as proving that they are. All right, time for a real challenge. So far, the evidence has been laid out for us, but sometimes a detective has to dig for a missing clue before they can solve the case. Let's see what happens when there's a twist. At first glance, this one looks tough. We only have two angles for triangle DEF and only two for triangle PQR. We can't use our AAA rule because we're missing a piece of evidence from each triangle. Or are we? We just have to remember one of the fundamental laws of geometry. All three angles in a triangle always add up to 180 degrees. So let's find that missing angle. In the first triangle, 180 minus 70 minus 80 leaves us with 30 degrees. In the second triangle, 180 minus 80 minus 30 gives us 70 degrees. We just found our hidden clues. And with those new clues, the whole picture becomes clear. Angle D matches P, angle E matches Q, and our newly discovered angles, F and R, also match perfectly. What looked like a dead end was actually a perfect AA case just waiting to be solved. So we've solved a few puzzles, which is cool, but why does any of this matter in the real world? Well, this kind of detective work lets us measure things that would be pretty much impossible to measure otherwise. Think about this problem. There's a 6-meter tall pole and it's casting a 4-meter shadow. At the exact same time, a big tower nearby is casting a 28-meter shadow. How in the world do you find out how tall that tower is without actually climbing it? The secret is similar triangles. Here's how it works. Since the sun is super far away, its light hits both the pole and the tower at the same angle. Boom, that's one pair of equal angles. Then both the pole and the tower are standing straight up, making a 90-degree angle with the ground. That's our second pair. So by the AA rule, the two triangles formed by the objects and their shadows are similar. And that means we can set up a proportion. The pole's height over the tower's height equals the pole's shadow over the tower's shadow. You solve that simple equation and there it is. The tower is 42 meters tall, and we figured that out without ever leaving the ground. That's the power of this stuff. So the next time you see two shapes that look alike, you'll have the tools to figure out if they're truly related. You'll know how to prove it. Case closed.